click next, and now here you select this full adder, because this time we are making the this test bench for this full adder. So click next, click finish, and you will see this window that where you can write this test bench. So in this case we need to add 2 bits. So let this x so x be 0 and this y be 1, and this carry in, or the input carry, or the carry from the previous edition, be 0, right? So we want to add these 2 bits in the first instance, and then in the next instance we want to add maybe 1 1, and then we want to add, maybe let's make a truth table. So let's make it 0 0 first, and then 0 0 1, and so 0 1 0. So this way you can make sure you've listed all possible input combinations. So I'm just copy pasting and then changing. So, and now, so two input combinations still remaining, the 0 1 1 1 0 and the 1 1, right? So every 100 nanoseconds the input change, and we get a new input, a new set of inputs, and so every 100 seconds we will see, so our output should also change accordingly, right? So 100 nanoseconds, that is. So this time is in nanoseconds generally. So okay, so now we have made this test bench. Now it's time to save it, and then we click on this module, and then we click on simulation, and then we uh, run its behavioral check, or we compile it. So as you can see, again there are no errors. So now let's simulate the behavioral model. Let's see the inputs response for these inputs. So again you click on this fit to screen thing, and you see so these are the 3 inputs, x, y, and z are your inputs, and as you can see, for input 0 0 0, sum and carry are 0, and accordingly sum and carry change with change in the inputs, as you can see, so which you can verify, right? So so we have successfully implemented the full bit a full adder and simulate it. So now let's move to uh, implementation of a 4-bit binary adder, and that would involve the use of these full adders. So so here we are uh, again. So now we want to implement this 4-bit adder. As you can see, it has 4 full adders. So this FA denotes the full adders module that we have just made. So as you can see, first full adder needs a carry. So this is generally C0 is generally 0. So but every next adder needs a carry from the previous addition, right? So uh, so connection of these full adders is if you look at this diagram, is very simple. You just need to connect the carry out of the previous full adder to the next full adder as an input. So let's make Verilog, or write Verilog code for this. So let's again add a source, another source. So new source, and this time again select Verilog module, and now you write the 4-bit adder maybe. So 4. So let's name it 4-bit adder. Uh, right. Again, the directory should be same. Um, so this directory, this is the directory where we have made this project. So now again click next again, and you will end up here. So again, you need, so this, in this window you need to write the code. So uh, so this is our 4-bit full adder. So first we need to uh, call the full adder module, and uh, we need to and then we need to call another full adder module, and connect the output C, or the carry out output, to the carry in output. That is, in our case we have named it, used it Z instead of C out and C in, right? So so this 4-bit uh, full adder has basically, uh, if you look at it, 8 inputs. In fact, 9 inputs. C0 is also an input, external input, and so each of these full adders give you one 1-bit output. So it has 4-bit sum, and this carry is also part of sum. So it has 5-bit 5 outputs, and 8 or maybe 9 inputs. In fact, 8 input, because this is always 0. C0 is always 0, right? So uh, let's specify inputs and outputs. So let's first specify inputs. A naught, so A1, A2, and A3, right? And B naught, B2, B3, and B, in fact, B1, it should be B1, right? Okay, so these are the inputs. So I'm not using the array type variable, but in the next tutorials, we will also learn to use an array type variable that can have more than 1 bits. So instead of using symbol for each bit, we can have an array that can store more than 1 bits, right? And it has 5 outputs. So S0, S1, S2, S3, and C4. So let's write these outputs here: S0, S1, S2, S3, and C4, right? Uh, and we So now we need to specify which one of these are inputs and which one of these are outputs. So it's very simple. Output, write this output keyword, and then copy this first part of these variables and paste them here. And so these are your outputs and input. So this A0 to B3 are your inputs. So copy them here, and now you need to specify wires if necessary. So if you look back on this diagram, you see these wires. So these are the intermediate wires that you need, or the memory elements, where you need to store the output of this full adder, this second output, the carry output of this full adder, and another memory element to store the second output of this full adder, and so on, right? So this C1, C2, and C3 can be our wires. So let's go back. So C1, C2, C3. Okay, so now let's start writing the code. So